Greetings. My name is Alexander Villalobos, and together with my partner Angel Carrasco, we'll be walking through this presentation series, Project Proserpine, a sample return mission design. Pictured here is our team along with their duties, starting from the top, Alexander Villalobos as the team lead. Below to the left, Angel Carrasco as our MATLAB specialist. To his right, Andrew Frazier as a free flyer specialist. Below them, to the left, mission specialists Kelly McInnes and Bimaya Jayaratne. To their right, technical analyst Jason Anaya. And together, we make up Project Proserpine. Our outline encompasses all the topics we will be discussing in this presentation, from mission objectives, the introduction, modeling assumptions, including trait studies for vehicle selection, our calculations and analysis, our final design of the Proserpine mission, a summary showing we have met all mission requirements and objectives, and lastly, an appendix to show all of our data and calculations used for our mission. Our mission objective for this project was to design a full mission from Earth departure, scheduled between the years 2025, but no later than 2035, to Earth return with a total flight mission duration of less than 15 years, with scheduling of events including rendezvous with Ceres, descending, landing, and ascending from the surface of Ceres. Through our findings, our spacecraft will be launched on the 15th of July of the year 2031 at the 18-hour, 24 minutes, 54 seconds of that day, and the entire mission duration will last approximately 5,454 days, which we will go more in detail in our final mission design. Our mission will be a follow-up to the Dawn mission launched by NASA. This spacecraft will land, collect samples, and return the samples back to Earth for further analysis that will help us understand the formation of ocean worlds. This will help us decide if this dwarf planet is potentially habitable. Key results were used to initialize our design and provide a path on how to tackle this project. Using the position vectors demonstrated here on the slide, together with the time of flight and the SLS Block 2 curve, which is shown here on this slide to the left of the free flyer trajectory, we came up with the C3 value and initial mass statement, which we then took and input in free flyer, resulting in the trajectory shown here. With a large C3 value, we knew that would be the first value to attack through trajectory analysis, flybys, and pork chop plots or lists, which would then lead us to improve the launch mass of our spacecraft while not hindering the launch vehicle performance. This mission, inspired by Dawn, will be explained in the following slides. Our thought process and mission design that we have developed with not only the tools provided to us, but the implementation of the theories and concepts learned in class as well. The software we utilized are explained in further detail here in this slide. MATLAB was used for the development of pork chop lists for the determination of the orbital elements of the spacecraft launch and return. JPL Horizons was used to collect the ephemeris of both Earth and Ceres. FreeFlyer was used to design and execute the mission profile departure and return. Trajectory Optimization Tool was used to create a Mars flyby and confirm the dates with MATLAB. Modeling assumptions were made using trait studies in order to help us initialize the design of this mission in the most efficient way possible. Some orbital assumptions were made as well and will be covered in the following slides. A trait study was conducted on 4 launch vehicle configurations to determine the best launch vehicle for this mission. Our objective was not only to find a launch vehicle that suits the desired payload, but meets the requirements of the mission, such as optimized performance at a minimal cost and expedient schedule. The considerations made for our trait study included delivering the payload to Ceres, having a launch vehicle that could provide a capture burn, and having a vehicle with a large enough fairing to ensure our spacecraft fits inside the fairing. The launch vehicles that we considered were the Atlas V, Falcon Heavy, SLS, and Delta IV Heavy. While the SLS is by far the most expensive, it can deliver the largest payload possible for this mission, along with having the largest fairing diameter. We were able to conclude that the launch vehicle that best meets our requirements is the NASA Space Launch System because it has the best payload delivery. However, considering the other vehicles, if the SLS were to be cancelled or our mission were to go under budget cuts, the next best would be the Falcon Heavy Expendable. Now I hand it off to my partner Angel Carrasco, who will go over the rest of the presentation. Thank you.
For our payload, we decided to do research on 3 existing spacecraft that have performed similar functions to what we need for our current mission. We decided that InSight, Curiosity, and Dawn all had similar functions on their missions to what we need to meet our requirements. The data collected from the Dawn mission prompted us to choose payloads based off of their available instruments because of the desire for the mission to be able to drill on the surface of Octar, capture images from the surface of Octar, and to be able to analyze the atmosphere for the existence of water. After performing a trade study, we found the best match for a lander for the mission would be the Mars InSight, which had the closest set of instruments needed as well as a smaller mass. From the propulsion trade study, we will determine the propellant that our spacecraft will use. Our requirements were that the spacecraft be able to make instantaneous velocity changes. Thus, we went with a hypergolic propulsion system. The Lyros 1C engine provided the highest specific impulse for our needs. For assumptions, we assume negligible delta V when the spacecraft enters Ceres so that we can enter at any inclination. Two-body motion was also assumed. We determined our initial mass from the C3 value we determined of our trajectory from Earth to Ceres. The propellant mass for certain maneuvers was determined from the rocket equation given spacecraft delta V's. The final mission design required a Mars flyby before reaching Ceres and a total mission span of nearly 15 years and a return to Earth mass of 1,500 kilograms, of which 1,270 is the spacecraft and Ceres sample. The mission never goes under 0.6 AU. Earth departure shall occur in the year 2031. We'll have a Mars flyby in 2032, where it will then reach Ceres in 2035. A landing module will then land on the surface in 2035 with a retrieval of the module with samples in 2045. The spacecraft will then depart Ceres in 2045 and arrive back to Earth in 2046.